The classic movie Good Will Hunting fittingly follows Will Hunting. No, not that kind of hunting. Played by Matt Damon, an MIT janitor with an eidetic memory that provides him with an affinity for high-level math, reportedly at the level of a genius. A professor at the school posts a short set of problems that he hopes a few students may solve on their own time. Long story short, Will discreetly solves the quite challenging problems on the board while cleaning, along with an even more challenging problem once it has been posted. After identifying Will as the culprit, the professor ropes him into a tumultuous working relationship involving research, job prospects, and various counselors. But how deserving was Will of this hype, really? Here, with Brendan narrating and me writing, we explore the first set of problems that Will solves and the mathematical theory behind them in order to answer our motivating question. How good is Will Hunting? Brendan, take it away.
Thanks, Luke. Starting with problem 1, we're tasked with finding the adjacency matrix A of our graph. Adjacency matrices are a pretty fundamental concept in graph theory that we've been over, so we won't go over the details too much, but it's important to note that 1 is adjacent to 2 and 4, 2 is adjacent to 1, 3, 3, and 4, 3 is adjacent to 2 and 2, and 4 is adjacent to 1 and 2. Because our graph isn't directed, we end up with a nice matrix that's symmetric across the diagonal, as shown. This symmetry ends up being helpful for some arguments we make later involving linear algebra. Next, for problem 2, we're tasked with finding the matrix given the number of 3-step walks in our graph. To put into simpler terms, this means that we must find the matrix L such that L sub ij gives the number of walks of length 3 from I to j. Towards the solution to this problem, we present the following proposition. This states that a to the n summarizes the walks of length n for all entries ij. We've already proven a similar statement within the course, but because our graph contains multiple edges between the same vertices, we'll go over a sketch of the proof of this proposition. This proof involves inducting on n. To ground this proof, we'll go over the base cases in a little more depth. For our first base case, it trivially holds that our walks of length 1 will just be the entry of the adjacency matrix A sub ij. For our second base case, we look at our number of ij walks of length 2. Fixing some I and j, we can split our walks of length 2 into 2 walks of length 1 from I to I prime and I prime to j. Summing over all possible I prime, we observe that our resulting answer is our ijth entry of the matrix A squared. Thus, looking at our whole matrix, we see that our proposition holds for our second base case. Next, we go over a quick summary of our inductive step. Supposing our proposition holds for some k, we look at our walks of length k plus 1. Like in our second base case, we can split our walks of length k plus 1 into walks of length k and walks of length 1. Further, from our first base case, we know that a to the 1 represents our walks of length 1. Thus, to enumerate all possible walks, we take the products of these two matrices, which comes out to a to the k plus 1, and we have shown that our inductive hypothesis holds. So, applying our proposition, our answer comes out to be a cubed, which after a bit of off-screen math, comes out to be the following matrix. Moving on to problem 3, which bounces off of problem 2, we must find the generating function for walks from I to j. A couple questions might come to mind when you see this problem. First, what the hell is a generating function? And second, what can we do with it? We'll get to those questions in a minute, but first it's helpful to provide context based on the problem. We know from our previous problem that a to the k represents the summary of all of our walks from point I to point j. Taking a specific I and j, we can look at one of our walks within this matrix. However, a to the k can take quite some time to compute, especially for large k. Further, if we want to look at trends over all k, this computation becomes even more cumbersome. Particularly, if we want to analyze the asymptotic trends in our walks as k approaches infinity, we need a method to be able to compute this. Generating functions not only provide a means to analyze these trends, but also have properties that allow them to be simplified in a way that vastly reduces the number of computations required. In this problem, these properties interact interestingly with Cramer's rule, which is normally quite an expensive process as well. However, given that we are only asked to determine the single element of a matrix, Cramer's rule becomes quite handy for reducing the number of computations required. Formally, a generating function encodes an infinite sequence of values as the coefficients of a power series. We see that this function has the form f of x is the sum over all I of a sub I times x to the I. Here, a sub I is the element of our sequence, and x to the I is our arbitrary variable x for which we have made a the coefficient. To summarize how we will solve this problem, first we will find our generating function in terms of our walks from I to j. Next, we will find the value to which this function converges in order to find a simpler expression for our generating function. Intuitively, it seems like we would want to apply the formula for our generating function to the ijth entry of our term a to the n. However, as noted earlier, it is quite difficult to compute a to the n in order to find this entry. It is important to note that computing a to the n is involved each step of this process. Perhaps, towards a simpler solution, we can express our generating function in terms of a to the n rather than just the ijth entry. Thus, we're presented with a new problem of analyzing the convergence of our new power series involving all of a to the n. We notice that this function is not in the exact form provided by our formal definition. There's a matrix term, and we don't exactly know how to deal with that. There are rigorous analytical approaches to determine the convergence of a power series involving a matrix. However, given that we are in an introductory graph theory course, we've decided to focus on a more intuitive, algebraic approach that is appropriate for the class. If you'd like to dig into the analysis side of things, we've provided a couple of links below. These go over determining whether it is possible to find the convergence of a matrix power series, and then actually determining the value to which it converges. In our method, we simply seek to find an analog to the classical method of finding the convergence of a power series. Towards finding the convergence of our generating function, we define S sub n to be a finite matrix power series. This implies that our generating function will be the limit of S sub n as n approaches infinity. With a bit of wrangling of a times x and our definition of S sub n, we can come up with an expression that no longer contains the summation operator. Redistributing our variables and applying inverse multiplication, we can isolate S sub n to be in terms of a times x in the identity. Returning to our generating function in terms of S sub n, we end up with the following limit. Under two conditions, first, that the limit as n approaches infinity of a times x to the n plus 1 is 0, and second, that the inverse of the identity minus ax exists, then we have an extremely simple formula for our generating function. As Luke said, wow! Now, when are these conditions met? First, we must show that the limit as n approaches infinity of a times x to the n plus 1 is a zero matrix. We can note that this is the same as the limit as n approaches infinity of a times x to the n. It is fact in linear algebra that symmetric matrices are diagonalizable. Conveniently, our adjacency matrix without self-loops is symmetric. Thus, we can rewrite A in its diagonalized form, PDP inverse. By bounding the absolute value of x to be less than 1 over our max eigenvalue, we see that our limit as n approaches infinity becomes a zero matrix. Lucky for us, this condition does hold true for our adjacency matrix. Therefore, our first condition is met. Next, we must quickly confirm that the identity minus a times x is invertible. We can recall that a matrix is invertible if and only if 0 is not one of its eigenvalues. This is equivalent to saying the product of any eigenvalue in x does not equal 1. Given our assumption that the absolute value of x is less than 1 over the absolute value of the max eigenvalue, we know that this second condition must be true. Therefore, we are able to conclude that the convergence of our generating function is the inverse of the identity minus a times x. But how do we actually calculate the expression for this inverse? As promised, this is where Cramer's rule comes in. Recall that Cramer's rule states that the ijth entry of an inverse of a matrix is equal to -1 to the I plus j over the determinant of that matrix. Thus, applying Cramer's rule in our proposition from problem 2, we can conclude that our generating function for walks from I to j is the following expression, which is much simpler than calculating all of the a to the n ourselves. With most of our work done, and a few questions on how Will had this much space on his mirror, we move on to problem 4, which states that we must find the generating function of walks from vertex 1 to vertex 3. This simply involves plugging into the general formula we found in problem 3. Once again sparing all the gory details, by calculating our determinants, we can come up with an expression for our generating function for walks from vertex 1 to vertex 3, strictly in terms of x.
Thanks, Brendan. I'll take it from here. So, the question remains, how good is Will hunting? With a background in linear algebra, calculus, and graph theory, the rote computations that Will invoked to solve the problems were not spectacularly difficult for us. That being said, it cannot be ignored that one of the largest problems in mathematics today, and an even greater one when the movie was made, is not about theory at all, but equity. Will had no opportunity to gain a formal education past high school, and in spite of that major hurdle, he demonstrated a strong grasp on higher mathematics by finding such a simple approach to find the solutions that he could work out the computations on his bathroom mirror. So really, there's no question about it. Will hunting isn't just good, he's great. We hope you all enjoyed. If you're interested in seeing any of the works we referenced while completing our project, including other analytic and algebraic solutions to the problems, we've linked them